it's periodic in the sense that, so Mendeleev was able to predict the existence of new elements by saying, you know, here's silicon, there should be an element, germanium, well, he called it ecosilicon. It's very similar but different directly below it in the periodic table. And so that's what you can do with this periodic table. So the idea, is there a pointer? Oh, there's a laser.
Yeah.
Let's see how well this, well this works. I have a laser. So the idea is a 0 category is a set. A 1 category is a category. A 2 category, you want to think about weak ones. So those are called bicategories, and so on. So it goes off infinitely in this direction. It doesn't stop at n equals 2. But then there's an interesting trick that you can do. For example, you can take a category and you can look at a category that has only one object, a special case. So a category with just one object will have a set of morphisms. Of course, it will have an identity morphism. And then for any morphisms in there, you can compose them. So you get another morphism. So you get a monoid. You get a set of morphisms with an identity element, an associative multiplication, and so you get a monoid. So, sorry, no, I don't want to press the power off. What are you saying? No. So a category with one object is a monoid, and so you can think of a monoid as a set with some extra structure, or you can think of it as a category with a special property that it has only one object. And that's the pattern that you can continue on. So for example, when you have bicategories, so in general, a bicategory will have a lot of objects, a lot of morphisms, and a lot of two morphisms. But you can look at bicategories that have only one object. So a lot of morphisms, and then a lot of two morphisms. It's a little hard to draw, but you have two morphism goes between morphisms, so you can have things like that. So because there's just one object, you can forget about the object, if you like, and you say we have a bunch of morphisms and two morphisms, but you can shift your point of view. You can call these objects, we're doing a shift here, and call these two morphisms, call them morphisms. So in other words, we have a category where these arrows are objects and the double arrows are morphisms. So we get a special kind of category from this bicategory with one object. And that's called a monoidal category. So a monoidal category is a bicategory with one object, and the reason why it's called a monoidal category is because it's like a monoid. So in the monoid, I guess you can point to the blackboard. I've never done this before. So in a monoid, it's a set, but you can multiply elements. Here you have a category, but you can multiply morphisms. So that's usually called the tensor product. So these things, which we're now calling objects, you can multiply them. So for example, the category of vector spaces with a tensor product of vector spaces is a category where you can multiply objects, and it's a good example of a monoidal category. But then you can do the same trick again, because you started with a two category. You can say, I will repeat the trick. So this is some kind of category. Let's look at one of those that only has one object. And that's a commutative monoid, it turns out. So in other words, I'm taking a bicategory with only one object and only one morphism, and just allowing lots of two morphisms. So there could be many two morphisms from the identity to itself. The usual way you draw these things is that you do something like this. So we have this one object here that's always the same, the identity. Have lots of two morphisms, but the point is that because we're in a bicategory, we can compose those both horizontally, like this. This is something you can do whenever you have a bicategory. And you can also compose them vertically, like this. So you could say it's a kind of monoid where you actually have two multiplications, a horizontal one and a vertical one. But it turns out that if you run through the axioms of a bicategory, you see that that those two multiplications wind up needing to be equal, and they wind up needing to be both commutative. So you've probably seen this if you've studied categories, but there's a famous argument called the Ekman-Hilton argument, which I should show you if you haven't seen it. So I'm going to use some rules for bicategories without explaining them. So this horizontal composite, you can rewrite it this way. You just have to take my word that I'm using the rules for a bicategory correctly. So F is equal to F composed with the identity. This is the identity on the identity of X. Right, so this is the identity of X. It will have an identity two morphism, the identity of the identity. Similarly, G you can rewrite this way. And then there's a beautiful law in bicategories, which is called the interchange law, which says that we can think of this in two ways. You can think of it as we compose them vertically and then compose them horizontally, or we can think of it the other way. We first compose these two horizontally, then these two horizontally, and then we compose the results vertically. So if I think about it that other way, here I have F composed with the identity, I get F, and here I get G. And so so far I've proved, right, that the horizontal and the vertical composition are the same. But really what I'm doing is I'm taking advantage of the fact that in two dimensions you have enough room to start moving things around each other. And what I'm doing is I'm taking F and I'm starting to move it around G. And then we can continue the argument. The same sort of reasoning. Let's see. Is this what I want to do next? Yeah, I guess I want to do this next. Is that what I want to do next? I'm trying to keep moving F around. Yeah, that looks good. Yeah, and then that's equal to this. So I've succeeded in moving F 180 degrees around G. So not only are the two multiplications, the horizontal one, the vertical one, the same, they're commutative. They're both commutative. So we have a commutative monoid. Ekman and Hilton discovered this argument in topology, but it's really an argument that applies in any bicategory. And so, in some sense, this is the kind of thing that got me very excited about higher categories. It says that the commutative law, which we use all the time in mathematics, is a law that applies in situations that are at least two-dimensional. If we lived in a one-dimensional universe, you couldn't walk around somebody else. There wouldn't be enough room. So commutative structures would seem very exotic, and only mathematicians would think about them. But because we can take two piles of rocks and move them around each other, for us the commutative law for addition seems very natural. We actually live in a three-dimensional universe, but you only need 2 dimensions to get the commutative law. So then this pattern continues and becomes very elaborate and very interesting. So the idea is the kth row here, an nth column, will give you some particularly nice kind of n category, which I don't have a shorter name for it, unfortunately. It's a k-tuply monoidal n category, meaning that there are k different ways to multiply objects. So this example here would be called a doubly monoidal zero category, right? A zero category is a set, but it's a set with two multiplications, horizontal and vertical, and then they obey some compatibility relations, which I've illustrated there. And then something very interesting happens. If you start over here with tri-categories, you can continue this process. Look at a tri-category with just one object. Look at a tri-category with just one morphism also. Look at a tri-category with just one two-morphism. Maybe I should, for those of you who haven't ever thought about tri-categories, I should at least draw a picture here. So here's some objects, some morphisms, some two-morphisms. You can cheat. You can use the blackboard to draw a three-dimensional thing. You should think of it as a three-dimensional ball with one of these two morphisms as the front hemisphere and the other as the back. But we can draw it in a plane like that. So it turns out that if you look at a tri-category that's triply monoidal, it's still just a commutative monoid. Basically because you now have three different ways of composing these three morphisms. You can compose them like this. You can compose them by attaching the two-dimensional faces together, or you can compose them by attaching, the one-dimensional edges together, or attaching the two-dimensional edges together. So it's like this, but a little more elaborate. But you can prove that all those three ways have to be equal, and they're all commutative. So basically what that's saying is that at the level of sets, having a third dimension to move things around doesn't help you at all. You got to the commutative law using two-dimensional mathematics, and three-dimensional mathematics doesn't help anymore. And so James Dolan and I conjectured for various reasons that it stabilizes there, that you only have commutative monoids, and similarly that it stabilizes here and here and here. So there's a diagonal line below which you don't get any new kinds of n categories. There was evidence from homotopy theory, something called the Freudenthal suspension theorem, that made us feel confident that this was true, as well as just thinking about n categories. But we were in a funny situation because there wasn't really a definition of weak n categories at the time. So we couldn't even call this a conjecture because the terms in the conjecture weren't defined. So we called it a hypothesis. So it was called the stabilization hypothesis by us. And now various people claim to have proved it using various approaches to n categories. And the reason why I say claim is because I'm sort of working on other things now, and I haven't carefully checked to see if all these proofs are pleasing to me. But I'm sure it's true. I'm sure it's true, regardless of whether it's proved. Hello. Yes?
Is there any kind of stringent enough definition in which the conjectures is kind of either true or very surely true?
Well, there certainly are a number of precise definitions of n category now available so that you can make this question into a precise yes or no question. You have to be a little careful even in how you make the concept, the question precise, because you have to develop more clearly the relationship between these things and the things below. And you want to say that any one of these things I can turn into one of these things and vice versa. So there's some subtlety involved in making the question completely precise, even if you have a definition of n category. But I think people can do that in various degrees of sophistication. And Carlos Simpson, for example, has a proof in one definition. A way of making it precise. So I could talk about this a lot, because all of these different concepts are fairly interesting. Among category theorists, these four are very widely studied. Curiously, this one was discovered after this one, and that's because mathematicians don't really believe that they're living in three-dimensional space. If you've ever noticed how they get lost, so it turns out that they, in a braided monoidal category,